Okay, in this video we're going to look at 4 common cross-coupling reactions. The Stille reaction, Suzuki, otherwise known as the Suzuki-Miyaura reaction, the Negishi reaction, and the Heck reaction. So all of these reactions are most commonly performed with a palladium catalyst. And we won't specify what the details of this are, but it's normally a palladium 0 or palladium 2 catalyst. There's many different types that can be used. They all have something in common. We're making a carbon-carbon bond between 2 components where we normally have a leaving group or a halide or pseudo-halide on one of the components. So I've drawn an Rx in these colours here. In the Stille coupling, the coupling partner is an organostanane or an organotin compound. And by far the most common are tributyl stananes or tributyl tin compounds. And this is largely due to the commercial availability of the precursors to those compounds. You can use other components, but as I said, these are the most common. So the side product of this reaction is going to be the tributyl tin halide. And so it's just going to be a waste byproduct that we need to remove from our reaction mixture. Okay, so that Stille reaction takes organohalide or pseudohalide plus an organotin compound, makes a new carbon-carbon bond, and generates a tributyl tin halide or pseudohalide as the byproduct. The Suzuki or the Suzuki-Miyaura cross-coupling takes that organohalide, and then the cross-coupling partner is an organoborane. So, and that can come in a variety of different structural types. We do this with a palladium catalyst, but we also need a base for a Suzuki reaction. And the byproduct in this case is going to be the X group now attached to our boron. Okay, and the base is involved in that catalytic cycle as an important part of getting the reaction to go. And once again, we get our much needed carbon-carbon bond formed during that process. The Negishi reaction can be done with a number of organometallic reagents, such as zirconium, aluminum or aluminium, but most commonly it's with the organo-zinc reagents. So we would have an R2 zinc X. The X could be different, but for simplicity we'll just say X in this case on both the organohalide and on the organo-zinc reagent. So we get a new carbon-carbon bond, and the byproduct is going to be simply a zinc halide. So zinc X2. Okay, and that's a very useful reaction because organo-zinc reagents are normally actually quite tolerant to a wide variety of functional groups. So whereas more reactive organometallics like Grignard and organolithiums would react with many other functional groups that wouldn't be compatible with this chemistry. Finally, the Heck reaction is actually probably the oldest of these, but it is in some ways the most complex in terms of the mechanism. It takes an alkene as the cross-coupling component with your organic halide or pseudohalide. And the alkene is actually going to lose a CH bond to make our new CC bond. So overall, we're going to generate HX as our byproduct in that reaction. And that's the reason why we do the Heck reaction in the presence of base. Part of the catalytic cycle is that we need to remove a proton from the catalyst to generate this HX, and that's in the form of the conjugate acid of this base. So overall, the Heck reaction will add this R1 group onto this alkene. And I've shown one example, but we can have a variety of alkenes, and it just depends on the structure, and by looking at the catalytic cycle, we can work out exactly what the product of that reaction will be. But there are 4 of the most common cross-coupling reactions, showing you what are the components that go into the reaction, what are the necessary reagents, and in all these cases a palladium catalyst, and then what are the side products produced in each case.